Other very interesting metric, especially in binary classification, is called receiver operating characteristic curve, also called as ROC curve, and area under this curve. Again, this curve has a very nice, interesting history. This curve was actually designed by electronics engineers or electronics and radio engineers during Second World War. To predict how well their missiles are working. Okay, it has a very, very interesting history on how this curve was detected. This, if you see the name itself, right? Receiver operating characteristics, looks very electronics in its naming, right? So that's why machine learning is all about taking all the great ideas from all areas of science, from physics, statistics, electronics engineering, everything that is possible, and incorporating all of it to solve our problems. Okay, so let's understand what this is. Imagine if I have a data set like this, right? I have x1, x2, x3, x4, and x5. 5 data points. For each data point now, I have the class labels, right? So let's assume this is my x, this is my y, and let's assume this is my y hat, right? If the class labels for these 3 points are 1 and these 2 points are, the actual class label 0, 0, this is 0. Let's assume this is 1, this is 1. Okay, let's assume my model which does binary classification not only gives me the class label of plus or 1 or 0, right? It also gives me a score like a probability score. Probability score is one score, right? So probability score is one score. It could be any score here. A score that represents as follows. More the score, more is the chance that it belongs to class 1. That's all we care about, or vice versa, right? So if my model gives me a score like a probability score, probability score is one score that models can give, right? Let's assume my model gives me probability scores, right? For x1, my model gives me a probability score of, let's say, 0.95. Probability score that x1 belongs to class 1 is 0.95. For x2, let's assume it gives a score of 0.92. For x3, let's assume it gives a score of 0.80, which is very high. Actual label is actually 0, but it's giving a very high value. That's okay. Let's assume for this point, I get a score of 0.76 and 0.71. First thing you have to notice is I have sorted my data in decreasing order of y hat. This is in decreasing order of y hat, right? So the first step in plotting ROC curve, the first step is take all of your data and sort it in decreasing order of y hat. Once I sort it in decreasing order of y hat, what I'll do here is I will do something called thresholding. The second step is called thresholding. So thresholding works as follows. Okay, I can take any value here. I can take 0.95. In the first step of thresholding, I'll take the largest value here. And I'll say every point, I'll use this as a threshold, tau. Thresholds are often written as tau. Okay, I'll write it as tau 1. My first threshold is tau 1. When I take tau 1, what I'll do here is I will say that I will use 0.95 as a threshold and say every point which has a value, which has a yi hat of greater than 0.95. So my tau 1 is 0.95. Now my model finally will become if y hat is greater than equal to tau 1, then declare it to be class 1, else declare it to be class 0. Okay, so if I take my first value as my tau 1, for every value, I'll get some class labels 1 and 0, right? And for every class label, if I have 1s and 0s, I can compute their true positive rate and false positive rate. To compute true positive rate and false positive rate, what do I need? I basically need a y, this is y hat, right? What do I need? I basically have another y hat, okay, which says whether I just need class labels. I don't require probability scores. I just don't require probability scores. Now what am I doing? I'll take tau 1. When I say tau 1, all these points which have a value of greater than 0.95 will have a final class label of 1. So let me draw it here just to simplify it instead of not using the whole space that we have here, right? So here you have your x, Here you have your y, right? Here you have your y hat. Let's take x1, x2, x3, x4, and x5. Okay. The actual labels are 1, 1, 0, 1, 1. The actual y hat values are 0.95, 0.92, 0.80, 0.76, and 0.71. Okay. Now what I'm doing, I'm saying what is the class label? Okay, let's call it y tilde with tau1 equals to 0.95. Then this will become class 1. This will become 0. This will become 0. This will become 0. This will become 0. Corresponding to y hat or y tilde. This is called tilde. Okay. Y tilde given tau1. Tau1 equals to 0.95. Given these values, right? Here I have my actual y's. These are my actual y's. These are my predicted y's. Given actual and predicted y's corresponding to tau1, I can compute a true positive rate and a false positive rate, right? Next, I'll take my tau2. I'll take tau2 equals to 0.92. Then what will I do? Now I'll say, what is the y tilde given tau2 equals to 0.92? This will be class 1, this will be class 1, this will be 0, 0, 0. Corresponding to this, I can compute one more TPR and FPR. These TPRs and FPRs correspond to tau2. These correspond to tau1. Similarly, I can keep changing this. I can keep changing these thresholds. If I have n points here, I can have n thresholds. If I have n points here, I can have n thresholds, right? Now, if I have n thresholds, tau1, tau2, tau3, so on and so forth, tau n. For each tau, I can get an FPR and a TPR, right? I can easily get a TPR and an FPR for each of these ones, for each of these taus. Let's call this FPR1, TPR1. Let's call this FPR2 and TPR2. Similarly, FPR3, TPR3. So on and so forth. Now what I'll do is this. I will draw a plot like this. I will draw a plot where my x-axis is FPR. FPR can lie only between 0 and 1, right? Right? Similarly, TPR can also lie between 0 and 1 only. Right? It can't, of course. My y-axis is TPR. My x-axis is FPR. Now I have pairs of TPR, FPR. I have FPR1, TPR1, FPR2, TPR2, so on. I have such n values, right? I will plot them now. So when I plot them, I'll get some values like this. And when I connect all of them, I get a line. When I connect all of them, I get a line. Typically, if your model is sensible, right, you will get a line like this. This line is called the receiver operating characteristic curve. Okay. Now let me draw one more line here. This line here, this blue line here represents, this blue line breaks this whole region. This is like a square, right? It's breaking this whole region into two parts. This is half. So the area under this blue line. So area under my blue line equals to half. The total area is 1, right? Because this range is 0 to 1, this range is 0 to 1. Now, the area under the curve, because my curve is this is my receiver operating stick. This is my receiver operating characteristic curve. It's a tongue twister. Let's just call it ROC. Okay. So this is my ROC curve. And I can say my area under ROC curve, it's often written as area under curve for short, is basically the total area under this whole curve. The total area under this curve, right? This area under curve can lie between 0 to 1. And 1 means it's very good. So the higher, the better. 0 means it's terrible, right? So this is what is called the receiver ROC curve. Let's put it that way. Okay. And this is a metric called AUC. Of course, if you don't want to see images, you can just say AUC of my model is this much. And this is only useful for binary. This is only useful for binary classification, not for multi-class classification. There are extensions of ROC to multi-class, but in general, we typically use it only for binary classification. Now comes the fun part. You might say, why did we do all of this crazy work, right? Because AUC has a very, very nice idea. Now look at this. AUC has some brilliant properties. One is, if you have imbalanced data, remember, there are a lot of course, downfalls of AUC also. If you have imbalanced data, your AUC can be high. AUC can be high even for a dumb model. So AUC is impacted by imbalanced data. AUC can be high or a very simple model. Okay, even very, very simple, forget about dumb models. For a very, very simple model or a simple model. Very, very simple models which are not very useful can have very high AUC if your data is imbalanced. I'm not proving this, but I recommend you to play with this idea and prove it for yourself. It's not very hard, by the way. Okay, that's the first property. Second property is, if you look at it, AUC did not care about the actual values here. AUC only cared about the sorting of this. So AUC is not dependent on the yi hat scores themselves. It only depends on the ordering. So imagine if I have two models, right? Imagine if I have two models, x1, x2, x3, x4, x5. Let's assume I have 5 data points, and this is 1, 1, 0, 1, 1. These are my y's, right? Suppose this model gave me a value 0.95, 0.92, 0.80, right? 0.76 and 0.71. Suppose this is model 1. Suppose I have another model M2, okay, where this value is 0.2, where this value is 0.1, where this value is 0.8, where this value is 0.7, and where this value is 0.6. For both models M1 and M2, because the sorted order is the same, your AUC for M1 is exactly same as AUC for M2. Because AUC doesn't care about the actual scores themselves. It only cares about the ordering. Because if you notice, we have not used the scores anywhere exactly. We have just sorted them. We have only used the scores to sort. Instead of 0.95 to 0.71 here, if I have some other values like this, right? These are completely different values from this, but the sorted order is the same. So AUC is only dependent on the order. It's not at all dependent on the actual values themselves. So the AUC for model 1 and model 2 will exactly be the same. This is a very important property of AUC, right? AUC is not dependent on the actual scores. It only depending on the ordering of the scores, ordering of the data. Right? AUC is often used in machine learning a lot, especially for binary classification, right? And the interesting thing with AUC is AUC typically only cares. Look at there's a very nice property of AUC again. Sorry, I completely forgot to mention that. Okay, so if you have a binary classification data set which is completely random, which means given a point xq, I randomly decide it's 0 or 1. Such a model is called a random model. Suppose if a model is random, right? It's not dumb, it's random. So it does a coin toss and decides whether it's class 1 or class 0. If a model is random, right? This is your FPR and this is your TPR in your ROC curve. Your ROC curve, if a model is random, not dumb, remember, it's not dumb, it's a random model. Okay, then the ROC for that random model will look like the straight point, the straight line. So the AUC of a random model, will be exactly 0.5. This is a very, very important property of AUC. AUC of a random model will be 0.5. Okay, there is another property. Suppose you trained a model M. Suppose you trained a model M and you plotted the ROC. Okay. Suppose you plotted the ROC. Okay. This is the random line. So you computed the AUC of model M, and let's assume you got a value of 0.2, which is worse than random, right? Which is worse than random. Because a random model, so what does 0.2 mean? 0.2 basically means that your AUC curve looks like this, right? Everything above this line means it is a good model. Everything below this model means it's worse than random. So as soon as you see AUC values, see, if you see an AUC value between 0.5 to 1, you are like, okay, this makes sense. If you see a value of 0.5, you know that the model is doing nothing sensible. It's just a random model. Now, if you see a value from 0.5 to 0.5, what do you do? The answer is very simple. The answer is extremely simple. This happens, by the way, sometimes, especially if you've done some mistake in your modeling. Then, if your model returns, if your yi hat equals to 0, just change the class label into the opposite of it. If your yi hat equals to 1, instead of, so that's what, by completely changing the class label. Okay, whenever it outputs 0, whenever the model outputs, so you have your model, you have your x cube. If the model outputs 0, change it to 1. If the model outputs 1, change it to 0. By doing this simple swapping, this is the simple swapping, right? Or simple changing of the class label in a binary class. By just doing that, if your original model has an AUC of 0.2, this modified model wherein you're just swapping, this is a simple swap operation or a switch operation if you want to think. You're just switching it. You're switching 0 to 1, 1 to 0. Okay. That model has an AUC of 1 minus 0.2, which is 0.8. So if you ever see a model with an AUC of less than 0.5, just switch or swap the class label. Swap the class label. And when you swap the class label, you get an AUC, which is 1 minus this value. In this case, 1 minus 0.2, which is 0.8. 0.8 is good, right? So this happens sometimes, especially when you've done some mistake in your modeling. So whenever you see a value between 0 and 0.5, by just swapping these class labels, you can get a good model. So whenever you see anybody reporting a value AUC less than 5, it means something is wrong in the modeling. Just swap the class labels and you'll get a value which is greater than 0.5. 0.5 basically means random. Anywhere between 0.5 to 1 means it is good. But as usual, this important part is AUC is not dependent on the actual probability scores. It only depends on the ordering. For imbalanced data, there are cases, not always. There are cases where AUC can be high while the model is not very good, right? So this is very important. We'll see some other very interesting techniques later on how to use probability scores themselves very creatively.